I'll post that tonight. Hopefully it'll be less than 10 minutes. So the first question, this is the second mock test that I'm recording so that you can study for the real test on Thursday and Friday, which you will have, and you'll be allowed to write it for at least an hour's worth of the class. Or whatever you need. Probably you're going to end up needing the whole class if experience has anything to say in this. So the first question is, what is the maximum number of electrons in an atom that can have the following quantum numbers? So they give you a set of conditions. In A, n equals 2, m sub s equals negative 1/2. So what we did, we had here n equals 2, m sub s equals negative 1/2. I wrote the electron shell filling mnemonic here with the maximum number of electrons that are allowed in each orbital, just to give you some background to help you remember. Now normally in a 2s orbital you can put a maximum of 2 electrons. In a 2p orbital you can put a maximum of 6. So in a number 2 quantum number you can get a total of 8 electrons. But they've put a condition on it. They say only the negative 1/2 m sub s quantum numbers are allowed. So that automatically slashes the number in half, because m sub s can either be plus 1/2 or minus 1/2. So if you only put the conditions of negative 1/2, you decrease it down to 4 electrons. So only 4 electrons can be put in the orbitals if m sub s can only be negative 1/2. In question B, it asks, if n equals 5 and L equals 3. N equals 5, L equals 3. Here's what you can put in the 5s orbitals. But when L equals 3, you're basically sticking to only the f orbitals. And you can put 14 electrons in f orbitals. So that's the answer, 14. I started listing them here. You don't have to do that. But if it helps you to get the answer, go ahead and do whatever you like. When you have L equals 3, which is what is here, then m sub L, which is plus or minus L, is going to have all the values from minus 3 to plus 3. That gives you 7 numbers. Negative 3, negative 2, negative 1, and so on. And in each one of those, you can put 2 electrons. So that's 14 electrons. That's how I got that number 14. I need a cameraman. That would be nice. Thank you. So for part C, no, it's the wrong one. Part C, the boundary conditions now are n equals 4, L equals 3, and m sub L equals negative 3. So I just listed all the possibilities for the values of L. So when L is equal to 0, it's an s orbital. When L equals 1, you get a p orbital, and so on. And all the maximums that you can find in each orbital. But now let's look at the conditions they've imposed. L equals 3, so you're going to be stuck with this, the 4f orbitals. And on top of that, m sub L has to be negative 3. So you don't have any of the possibilities like negative 2, negative 1, 0, and so on. So that it basically forces you to have only 2 electrons, the ones with plus m sub s plus 1/2 and m sub s minus 1/2. And here's the conditions: 4, 1, 1. No, sorry. 4, 3, negative 3, 1/2. 4, 3, negative 3, negative 1/2. Because they force you to have m sub L equals negative 3 with L equals 3. And so you only get 2 electrons. So the answer for this question is only 2 electrons will be found under those conditions. In D, they ask, n equals 4, L equals 1, m sub L equals 1. Again, I listed the possibilities for L. And with L equals 1, you could have 6 electrons in there because you'd have minus 1, 0, and plus 1 for m sub L. But they've also established that you're only allowed to have m sub L equals to 1, so that it gives you only 2 possibilities, the ones that are afforded by the fact that m sub s can be plus 1/2 or minus 1/2. So again, 2 electrons is the limit for this set of conditions. In question number 77, they ask, in June 2004, the Cassini-Huygens spacecraft began orbiting Saturn and transmitting images to Earth. The closest distance between Saturn and Earth is 746 million miles. Transmitted signals what is the minimum amount of time it takes for the transmitted signals to travel from the spacecraft to Earth? So we take 746 million miles, the distance from Earth to Saturn at that particular time, convert it to feet, convert it to inches, convert it to centimeters, convert back to meters. That's how many meters it is. And then we use the rate equation. Rate times time equals distance. We solve for time by transposing the r. Here's the distance we just converted to. There's the speed of light. And that's how many seconds it would take for that beam of radio wave energy to reach the Earth from Saturn, from the satellite. And then we converted it from seconds into hours, and you get 1.11 hours. Or if you prefer, you can just state it as seconds, 4.00 times 10 to the 3 seconds. Question number 3, which is 82 from the book. The light-sensitive substance in black and white photographic film is silver bromide, AgBr. Photons provide the energy necessary to transfer an electron from bromide ions to silver cations to produce Ag and Br, thereby darken the film. A, if a minimum energy of 2.0 times 10 to the 5 joules per mole is needed for this process, what is the minimum energy needed by each photon? B, calculate the wavelength of the light necessary to provide photons of this energy. C, explain why this film can be handled in a dark room under red light. So here's the amount of energy that you need, and this is the reaction. So you see bromide is giving that electron to the silver cation, so that you end up with oxidized bromine and reduced silver, both of which help to darken the film. And so that much energy per mole divided by Avogadro's number of atoms per mole gives you how much energy per atom. So that energy would have to be provided by one photon. So that's the energy of one photon. We're going to plug it into the Planck equation rearranged for frequency. So here's the energy, here's Planck's constant, there's the frequency that you get as an answer. Then we take that frequency and plug it into the lambda nu is equal to c, where c is the speed of light. This is the frequency of the light, and that's the wavelength of the light. We're going to solve for the wavelength. Speed of light divided by frequency. Here's the speed of light, here's the frequency, and there's your wavelength. And then we converted it to nanometers. 598 nanometers is a photon of visible light, because our eyes see between 400 and about 750, where 750 would be the red end of the spectrum. So as long as the light is longer than this wavelength, it will not expose the film. So that's why they put red lights in a dark room, because the red light is around 700 and it doesn't have enough energy to cause that reaction to take place. So the answer to part C is red light has a wavelength of 700 nanometers, which is below the energy level required to elicit the reaction if it is below the threshold frequency. So the photons are just not energetic enough to cause that reaction to happen, so you can safely expose the film to that light without changing the amount of exposure. Now, we're going to go over there, so you can take the phone, I'll take the computer. Okay, good. I'll just adjust it. Great, that's good. Tech production. Okay, so we have 88. An electron is accelerated through an electric potential to a kinetic energy of 18.6 kilo electron volts. What is its characteristic wavelength? Hint, recall that kinetic energy of a moving object is E is equal to 1/2 mv squared, where m is the mass of the object and v is the speed of the object. So the first thing I did was I converted, that's better, I converted electron volts into joules. So I looked at the back of the book or in my calculator, because it's embedded in the memory of the calculator that I have, which is a Sharp calculator, but any scientific calculator will have it. And at this point, guys, you should be getting a scientific calculator, because when we do the exam, you're not gonna be allowed to use your phones. Because that, you could cheat with the phones, because you can use Siri. So you gotta have a calculator on that day, and I don't lend my stuff, because I keep on losing calculators that way. So you gotta get yourself, invest the $35, it's worth it. And that way you can write the exam at your leisure. But I mean, I will always provide you with all the constants anyway. I'll write them on the board, or if I forget, you can ask me and I'll write it anyway. So it happens to be constant 37 in my calculator. And then I also looked up the mass of an electron, which is also embedded in the memory of my calculator. So 18.6 kilo electron volts multiplied by 1,000 electron volts per 1 kilo electron volt allows us to cancel kilo electron volts. You get 18,600 electron volts multiplied by the conversion factor into joules. There's the number of joules for that amount of energy, for this amount of energy. Then we plug it into the kinetic energy equation. The only thing we don't know is the velocity of the electron. So we rearrange the equation to solve for velocity, which we get to be the square root of 2 times the energy divided by the mass of the electron. Plugged in all the numbers, and I got this velocity for the electron. Then I took the velocity of the electron and I plugged it into de Broglie's equation. Lambda is equal to Planck's constant over the momentum, which is mass times velocity. This V is not frequency. It's tricky. When you use de Broglie's equation, you got to use V for velocity. I know it's maybe I should have put VE, like velocity of electron or something. Anyway, Planck's constant, mass of the electron, velocity of the electron. You get a wavelength for the electron, and then I converted it to picometers. I converted it to picometers by multiplying by 10 to the 12 picometers for meter, allows me to cancel meters. The last question is 95, was the bonus question, and in that one, we found out that 600 megahertz.
Good morning, staff and students.
We'll cut it short here.